So by popular request, I'm going to do some number theory because some of you were thinking about doing it for your project. And I thought that instead of writing, I keep thinking of number theory questions, the solutions to which will kind of take 10 to 15 minutes. Because, basically number theory is slightly tricky to do. You're switching between the naturals and the integers and that sort of thing. So I thought I would just randomly try some number theory questions. And I found some old book by Sierpinski containing a bunch of number theory problems, and I thought I'd try one of those. So let's go. Import tactic. The question was for which positive integers n does n plus 1 divide n squared plus 1? So let me tell you that Lean isn't going to work out the answer to that question. So there's the question. Actually, we could make that, there we go, like that, couldn't we? So let's try the maths. I know how to do it mathematically, so here's the trick. Here's the trick. N plus 1 divides n squared minus 1 because it's n plus 1 times n minus 1. So if it divides n squared plus 1, then it divides the difference, right? N squared plus 1 take away n squared minus 1, which is 2. And n plus 1 is at least 2, so n plus 1 equals 2, giving n equals 1 as the only solution. So there you go. That would convince most mathematicians, I should think. So now we've got to convince Lean, so let's try it. So example, n is a natural number, and the hypothesis on n is that it's positive. And we've got another hypothesis, which is that n plus 1 divides. How do you do divides? You don't do it like that, because that's set theory notation. You do it like that, slash divides, and it's, I don't know if you can see, but it's a slightly bigger, at least in my font, is it? No, it's not. It's a completely, yeah, that one's slash divides and that one's regular divides. So it's impossible to distinguish from the pipe symbol on your keyboard, but it obviously is completely different to that because it's slash pipe symbol. N squared plus 1. Wait, that's not a hypothesis. This is going to be n squared plus 1 divides n squared plus 1 if and only if n equals 1. Begin, sorry, end. So this is going to be slightly painful, I think. So we could split. Well, sorry, the first part. And the second, the easy way is this, right? So we could do Rintro Ruffle. So n equals, so we could do intro h, then we'd have the hypothesis that n is 1, and then we could rewrite h. But Rintro Ruffle does both of those things in one go. And now I think for division, I think norm num will do this. Yes. So that's the easy way. We show that it does work for 1, and now we've got to prove that it doesn't work for anything bigger than 1. So intro h. And so now I need to tell you something about the API for this division symbol. So I'll show you. Look, have h2. I claim that. Okay. So, we run into our first problem, which is that I think that proving n plus 1 divides n squared minus 1 is going to be a bit annoying because we are working with the naturals. So I could cheat here and just change that natural to an integer. So that would make the question much easier. But let me show you how to solve it in its current state. Can I zify? So there's a zify tactic. Let's try zify at 8. Does that work? Oh, that's a shame. Okay, let's not worry about that yet. But let me zify that. So the issue is I want to treat n as an integer, so I'm going to do this. N as an integer, plus 1. I don't need the brackets. N as an integer plus 1 divides n squared minus 1. I don't have to go on about more integers now. You see, you can see the goal, right? So let me. It's always good to have just one goal. So what's going on here? You see the difference between h and the goal. The goal has got this little up arrow, and what's going on there is that's the integer. That's the integer n. So the up arrow is the map, the invisible map from the naturals to the integers. So how does one prove that something divides something? Because of course, the answer is it's factor n squared minus 1 is n plus 1 times n minus 1. But you see that factorisation wouldn't work over the naturals because minus is a pathological operation. Let me just, for those of you that don't know what I'm talking about, look, if I eval 2 the naturals minus 3, I get 0. You see, so there is a subtraction defined on the naturals, but it's pathological. Whereas if I evaluate 2 as an integer minus 3, I kind of don't like the fact that the subtraction symbol is used for that bizarre operation. I mean, if you do a take away b and b is bigger than a, you just get 0. But if you do it with the integers, you get the correct answer of -1. The point is that you can see the type of subtraction. Subtraction is notation for has sub dot sub, and the type of has sub dot sub is alpha to alpha to alpha, which means you give me 2 naturals and I'm forced to give you a natural. So 2 minus 3, it prints out 0. So we need to be working with integers. So that's why I've done this, and now I'm going to prove. So the question is, what's the definition of division? So we can unfold. I mean, I'll show you how to work it out. Set option. Let's switch off notation. So now we can see what the thing is called. So it's called has divide dot divide. So we can unfold has divide dot divide. And now let's put notation back on again. And there we go. So the goal is definitionally equal to there exists a c such that n squared minus 1 is n plus 1 times c. And so because the goal is exist, we can solve it with the u's, right? We can do u's, or we can make progress with the u's. And so we can use n minus 1. And now this is an identity in ring, so ring will do this presumably, yeah. So there we go. So now we know that n plus 1 divides n squared minus 1, and we also know that n plus 1 divides n squared plus 1. But it's not. It's not the same n. There's an integer n and a natural n. So now I've got to try and figure out how to change this. I mean, it's a great shame I can't zeify it. Zeify at h, that really doesn't work. Failed. So what about rewrite divide? If I'm desperately trying to, is that not a thing? Divide. I just want the definition of divide. Oh no, this is all kind of hopeless. I'm just going to play with this. Unfold has div dot div h. It has divide dot divide, isn't it? Has divide dot divide. And now can I do zeify at h? Right. See, now the zeify has worked, and now I can re-unfold it. Aha. So that's a bit rubbish, isn't it? And now I want to fold it back up again, of course. Change n integer plus 1 divides n squared plus 1 at h. Oh, it doesn't even work. Ha ha ha. Well, that's quite surprising that it doesn't work. What's going on? So as you can see, it's kind of a nightmare working with this. I mean, okay, all right, let's not use division. Let's do it this way. So intro H, and let's just. So I'm having trouble using division because it seems. Is it really true? Is it? I'm now tempted to I'm making a video. Let's just get on. I think I'm not going to use division because I'm finding it annoying to use division and naturals to integers. I mean, one could boost the zify tactic so that it would work for H, but we're not going to do that right now. I'm going to do case. I'm going to take H apart, so I can do that here. So H is definitionally there exists something. So let's rintro CHC there. So now H is n squared plus 1 is n plus 1 times C. And now let's do have H2. Let's just write what we want. N squared, the integer n squared minus 1 equals n plus 1 times n minus 1. There. And I can just solve that by ring. Colon equals by ring. And now I can I suspect I can zify HC now. Okay, great. So now we are, okay, so I've given up using division, and so now I want to prove, so now I do want to use division, because I want to use the fact that if something divides 2, it's less than or equal to 2. So my claim is, have H, we haven't got an H1 yet, so maybe that should be an H1. Let's have an H2. My claim is that n plus 1 divides 2. No, my claim is that the integer n plus 1 divides 2, and my proof of this is going to be that we can subtract H1 from HC, so we're going to use C minus N minus 1, right? There. And now I've got to use H1 and HC to prove this goal here, and it's kind of clear how we're going to do it. This is this is n plus 1 times something take away something, and so we need to sort of expand out that bracket. And that's going to be called mul sub, I suspect. Rewrite mul sub. Yeah, that's worked. And now I can rewrite, so I want to rewrite HC backwards and H1 backwards. So rewrite mul sub, comma, backwards HC and backwards H1. There. And now that should be ring. Bingo. So now we know that the integer n plus 1 divides 2, and so now I want to deduce that n plus 1 is less than or equal to 2, and so have H3, the integer n plus 1 is less than or equal to 2, and I suspect library search isn't going to work because it's not going to know that 2 is positive or something. Yeah, library search is first, so we need to guess the answer to this. Apply. It's going to be LE of Devud or something. Have we got one of those? Int dot. It's first thing. Int dot LE of Devud. Yeah, this looks good. We've now got 3 goals. We've got to prove that 2 is positive and n plus 1 divides 2, which is H2. So int dot LE of Devud. Yeah. It wants to prove that 2 is positive. And that's called 0 LT2 as far as I know. And then it wants to prove that n plus 1 divides 2. That's why we have 2 goals, not 1, because int le of Devud wants to eat the proof that n plus 1 divides 2, so I can just give it there, H2. There we go. So in fact we could even do colon equals this, I would imagine. Yes. So now what do we know? We know that n plus 1 is less than or equal to 2, and we know that n is bigger than 0. And I suspect Linarith won't do it. Linarith would have to be pretty smart to do this one. Oh, it does it. The reason I was pessimistic was that somehow we've got some integers and some naturals. This is the problem. Linarith would have to spot that the natural n plus 1 was less than or equal to 2. Maybe I should just show you how I was thinking that I would have to do this. Have h4 that natural n plus 1 was less than 2. And you see we have that, right? This is less than or equal to 2. This is sort of quite confusing when you don't know this sort of awkward difference between the naturals and the integers. It looks like that says h3, but h3 is a statement about the integer n, the integer 1 and the integer 2, and we want the natural one, the natural 2 here. So you can see this is it is h3, but exact h3 won't work, I suspect. Yeah. But you see these maps from the naturals to the integers and things are called casts. And so there's a tactic called exact mod cast h3, which does work. So I thought I was going to have to do that. Now, because now I would be confident that Linarith would work, because we know that n plus 1 isn't most 2 and n is bigger than 0. But Linarith is sufficiently smart that we didn't need to do that. So, that's it. Oh, there you go. Yeah, that's the end of the proof. So I guess I'm going to stop there. And there's some examples of how one does arithmetic in Lean.